Okay, so if the mass of the ice cube is 8 kilograms, then due to the principle of flotation, mass of ice, which is the object, must be equal to the mass of water displaced. So the mass of ice is 8 kilograms, and mass of water displaced will be density of water times the volume of water. Density of water is 1. Okay, or is let's use the mass in kilograms so that we can express the density to in. So if the mass is 8 grams, then it means the density of water will also be 1 gram per cm cube times the volume. Therefore, the volume of water that will be displaced will also be 8 cm cube. Okay, so it means that the mass of ice displaces a volume of water which is equal to its mass. The mass of the ice is 8 grams. Volume of water displaced is also 8 cm cube. So 8 grams of water will displace 8 cm cube of water. 10 grams of ice will displace 10 cm cube of ice. So a floating object displaces a volume of water which is equal to its mass. A floating ice displaces a volume of water, which is equal to its mass, which is equal to its mass. So here we had 8 grams of ice displacing 8 cm cube of water. If you consider maybe 20 grams of ice, 20 grams of ice, it would also displace the same volume of water because mass of ice must be equal to mass of water displaced. This is a principle of flotation. So 20 grams of ice the mass of water displaced must be the density times volume. Density of water is 1.0 gram per cm cube. And so the volume of water that will also be displaced will be equal to 20 cm cube. So whatever the mass is, it must displace equal volume of water. Please, class, are we okay? Are we okay here? Hello, give me feedback. Are you fine?
Yes, sir. Please, we are fine.
Okay. So this becomes the volume of water which will be pushed away. The volume of water which will be pushed away. And this is the volume which will be occupied by the ice. Okay. This will be the volume occupied by the ice. Now, volume of ice, when the ice melts, let me check. There's a question, so let me check on the question and then get back to you. Ella. So, Ella, all that I'm saying is that if If the mass of ice is x gram, it will also displace x cm cube of water. So 8 grams of ice will displace 8 cm cube of water. 20 grams of ice will also displace 20 cm cube of water. So whatever the mass is, please, when you join, mute yourself for me. I'm getting, okay, let me rather mute all. Okay. So whatever the volume, the mass, it will displace water, which is equal to its own mass. So a floating ice displaces a volume of water, which is equal to its mass. Okay. Now, when the ice melts, okay, 8 gram of ice, will melt to, or would produce 8 grams of water. 8 grams of ice will produce 8 grams of water. And don't forget, the density of water is 1 gram per cm cube. So if when melted, the mass will be 8 and the density of water is 1, then what will be the volume of the water formed? Look at it. Density is mass over volume. Volume would also be mass over the density. So when the 8 grams of ice melts, it will produce 8 grams of water, whose density is equal to 1 cm cube. Therefore, the volume of the water, of the melted water, would be the mass of water, which is 8 grams, divided by the density of water, which is 1 gram per cm cube. So the volume of water which will be formed after melting will still be equal to 8 cm cube. And this volume of water formed after melting is equal to the volume of water which is displaced. Okay, so initially, the ice will displace 8 cm cube of water, push it away, and that is the space occupied by the ice. When the ice melts and forms water, the volume of the water formed will also be equal to 8 cm cube. So 8 cm cube of space is created and filled by the ice. When it melts and the ice is no more, the ice turns to 8 cm cube of water. So the water would occupy the space or the volume which was occupied by the ice. So the water formed occupies the space or the volume which was occupied by the ice. By the ice initially. So the ice will create a cm cube of, or will displace a cm cube of water. And when it melts, its volume will still be 8 cm cube and will be filled by the water now. Please, are we okay? Are we okay now? Imelda, can you hear me?
Yes, please.
Okay, so this is the reason why the volume will never change. The volume of water after the ice is melted will never change. whatever the mass is, it will displace volume of water equal to its mass. And so when the ice melts, the volume of water formed is equal to the volume which was displaced by the ice. So it just fills the same volume and it becomes the same. Now, when I was marking, I gave some of you 3, I gave some of you 5, 4. This is because I saw statements like when the ice will displace volume of water which is equal to its weight. The volume of water displaced is not equal to its weight. It's not equal to its weight. But the ice displaces volume of water whose weight, okay, the ice displaces volume of water whose weight is equal to the weight of the ice. Not the volume of water displaced being equal to the weight, but the ice displaces a certain volume of water whose weight is equal to the volume of the ice. That is what must be said. And this is the reason why I deducted 1 or 2, depending on what you write. Frank.
So what if the hello?
Yeah, I'm listening.
Yeah, so what if the cup isn't filled to the brim? So would it add a volume to will the melted ice add volume to the
No.
water because it won't displace any water out?
No, what I'm saying is that whether filled to the brim or not, okay, when the ice melts, the volume will not change because the mass of the ice will be equal to the volume of water which is displaced by the ice. So if we had a 50-gram ice, it will displace 50 cm³ of water. So when it melts, the water formed will have a volume equal to the volume of water which was initially displaced. So whether filled to the brim or not, it will not change. Frank, are you okay? Frank, are you okay? Hello, Frank. All right, great job, teacher. Okay, Ella, ask your question.
What Liz is trying to say that what if like it's not filled to the brim, so if the ice melts, like no water will be displaced because the ice there's still space for the ice to
No,
occupy.
Ella, once you put ice into it, once you put ice into it, the ice will certainly displace a certain volume of water, okay? It will certainly displace a certain volume of water and will fill that space. So once there is ice, it will certainly displace a certain volume of water. That's what I'm saying. Ella, are you okay?
Yes, please.
So once you put in ice, the ice will displace a certain volume of water and will fill the space. Now, when the ice melts, the volume of water displaced must be equal to the volume of the melted ice or of the water formed. So it's like the ice creates a space which is equal to its mass, and when the ice melts, the volume of water formed as a result of the melting is equal to the volume of space created. So nothing changes. Okay. All right. The second question. The second question is that a piece of aluminum with mass 1 kilogram. So mass of aluminium is equal to 1.00 kilogram. And its density, the density of aluminium is 2,700 kilogram per cubic meter. In fact, I'm glad to say that almost 90% of you scored this question. Yes. So it means we are actually doing well. Almost 90% plus of you got it. This is suspended from a string and then completely immersed in a container of water. Calculate the tension in the string A, before the metal is immersed, and B, after the metal is immersed. So we are looking for before and after. Take acceleration due to gravity to be 10. Okay, so let's just have a sketch. This is a spring balance. Something is attached, aluminum block is attached to the edge of the spring balance. Okay. Now, the spring balance has a spring in it. The spring is like this. And springs operate on Hooke's law. Okay. Now, once it is attached to a support, this is the support. The tension within the spring is always directed to where there is support. So this is the tension in the spring. It is directed, tension is always directed to where there is support. The weight of the aluminum block would always act downwards. Now, if the weight of the block is not greater than, is equal to the tension, the block will never tear off. It would comfortably hang. But the moment the weight of the block is greater than the tension within the spring, then you realize that the spring would break and then the object will fall. If you've been observant, during weighing, when children are taken to weighing, okay, they are put in a cloth and then hung on a spring balance to determine their weight. All the time, the weight of the child is always equal to the tension within the spring, and so the child could comfortably suspend on the spring. Now, a day where the child drops, then it means the child's weight is greater than the tension in the spring balance. So when the child is comfortably suspended on the spring balance, then it means that the child's weight is equal to the tension in the spring. Under this condition, we say that the weight of the object or the child and then the tension in the spring are in equilibrium. Both are in equilibrium. So this is an equilibrium state. We'll look at Newton's laws of motion and you understand equilibrium state. Okay. So when the child or when the object comfortably is suspended on the spring balance, then it means that the weight of the object is equal to the tension in the spring. Okay, and this weight of the object is the weight in air. So when you are looking for the tension in a spring when the object is weighed in air before it is suspended or immersed in a liquid, then the tension is equal to the object weight, which is the product of the mass of the object and acceleration due to gravity. And the mass of the object is 1 kilogram. So 1 kilogram times acceleration due to gravity, which is 10 Newton, 10 meter per second squared. So it means that the tension in a spring under this condition is equal to 10 Newton. This is the tension in the spring before it is immersed in water. Okay, so the tension in the spring is equal to the weight of the object in air. Anita, are you okay?
Yes, sir.
When the object is immersed in a liquid, liquid has an upward force, which is the upthrust. Upthrust is always up. So its direction is always up. U. So when we total forces in up and down, we have the tension in the spring going up, upthrust also going up. And this must be in equilibrium. Balance must be balanced by the weight of the object going down. So it means that when it is immersed in a liquid, the tension in the spring would be equal to the weight, its weight minus upthrust. Let me open a new page. Okay, so when immersed, the tension in the spring will be equal to the object weight, which is 10 Newton minus upthrust, U. And upthrust is equal to density of the liquid times volume of the liquid displaced times gravity. We have the liquid is water, so the density is 1000. The volume of water displaced will be equal to the volume of the object since it is totally immersed. Okay, and this will be equal to the mass of the object divided by the density of the object. Mass of object 1 kilogram, density of object 2,700 kilograms. So we have the volume of the object giving us 1 over 2,700 times acceleration due to gravity, which is 10. In all, we have 1, 2, 1, 2. So we have 100 divided by 27. And class, what is 100 divided by 27? 100 divided by 27.
3.703.
3.703.
3.704.
Okay.
704.
Okay, so that is the upthrust in water. Therefore, the tension in a spring is equal to the weight of the object minus the upthrust, which is 3.704. And this must give us 6 point what? Plus 6 point what? Amel Anita.
6.296.
29 what?
6.
Newton. Yeah, so it isn't a difficult question actually to try. As I said earlier, a lot of you got it right. So let us solve questions on floatation. Okay, so I'm going to forward a question to the group. I've just done that. This one.
Yes, I've seen it.
Okay. So the question reads, please, the rest of you, have you seen the question?
Yes, sir.
Okay.
Yes, sir.
So
Yes, sir.
a uniform cylindrical hydrometer of mass 20 gram and cross-sectional area of 0.54 cm cube. So the mass of the hydrometer, we are told, is 20 gram. The cross-sectional area of the hydrometer, we are told, is 0.54 centimeter squared. Floats upright in a liquid. It floats upright in a liquid. If 25 centimeter of its length is submerged, so height submerged, height of hydrometer submerged, we are told is equal to 25 centimeter. Calculate the relative density of the liquid. We are to determine the relative density of the liquid. When the density of the liquid, of course, the liquid is water. So the density of the liquid, we are told, is 1 gram per centimeter cube. So rho in this case is 1.0 gram per cm cube. The question demands that we find a relative density, RD, of the liquid. I'm giving you 6 minutes to try this. Okay. Class, is that okay? So give it a try for 6 minutes, after which we will discuss it so that you mark whatever you were able to do. This is your problem. Start with. To those of you who just joined, the question is on the platform. The question is on the platform. So start with. 6 minutes. So the time is 10 by my watch is 10:32. So at exactly 38, I'm coming your way. Let me take attendance. Hello, come. Marilyn, are you there? I'll say it to you. Hello, Marilyn.
Sir.
Okay. Did you see my message?
No.
Oh, I sent you a message. Just check your phone. So you have 3 minutes more. 3 minutes. 3 minutes to make me proud.
Easy. Excited. Oh. Hmm.
Hello. Yes, your time is up. Oh, okay. I think Elikem's answer, and then who else? Yes, it's 1.48. That's true. Gideon, 1.022. Sorry, it's 1.48. Okay, let's look at the how. Gideon, I'm listening.
Sorry, what's your mistake?
Okay, so let's solve it. Let's solve it. Whilst we go through, please use that to mark whatever you were able to do. Okay, so we are to determine the relative density of the liquid. Relative density. RD can be expressed in different ways. One of it is the foundational equation is actually density of the substance, here of the liquid, divided by the density of equal volume of water. Equal volume of water. Okay, and the density of water, no matter the volume, if it's pure water, must be 1 gram per cm cube or 1,000. Elikem.
Sir, please, I can't see your screen.
Really? Please, is that a general problem?
No, please. No, sir.
Then Elikem rejoin and let's see, okay? Because it might,
Yes.
it might be a network problem. So RD is this. So it means that once the density of water is constant, 1 gram per cm cube, all that we require here is to determine the density of the liquid, and we can determine the relative density. Okay. Now, how do I do it? The hydrometer floats, and once it floats, the law of flotation must apply. Mass of the object, which is the hydrometer, must be equal to the mass of water displaced. Mass of the hydrometer, we have it. The mass of water displaced is equal to the density of water times the volume of water displaced. Now, the volume of water displaced is unknown, okay? But the volume of water this is a cylindrical in shape. So the volume will be equal to the uniform cross-sectional area times the height. height of hydrometer, which is submerged. Okay. Hello, please, is that okay?
Yes, sir.
Okay. So, okay, it's a liquid. So we don't know its density. We don't know the density of, so please let me correct this. It's a mass of water. No, it's mass of liquid. Mass of liquid displayed. So this is the density of the liquid times the volume of the liquid. So we have mass of the hydrometer equal to 20 grams. This is equal to the density of the liquid, which is unknown, times the volume of liquid displaced is equal to the cross-sectional area times the height of the hydrometer submerged. Okay. Density, which we are looking for, is rho, and area is 0.54. The height of hydrometer submerged is 25. Therefore, the density of the liquid will be equal to 20 divided by, please, what is 0.54 multiplied by 25? 0.54 multiplied by 25.
13.5.
Come again.
13.
13.5.
Okay. So this is 13.5. So when you divide 20 by 13.5, it's 1 point, 1 point,
1.48.
1.481. Okay. Please usually leave your answers in at least 3dp if you are not asked to run your figures. So this is the density of the liquid. And once we have the density of the liquid, it means that RD is equal to the density, which is 1.481 divided by the density of equal volume of water, which is 1. Okay, don't forget RD has no units. So we have 1.481 as the relative density of the liquid. I hope that is understood. Class, is that understood?
Yes, sir.
All right. Another question for you to try. Today we'll use question and answers just to finish this, and then we'll continue a new topic next week, on Thursday. So I'm going to forward it to the group. Yes, it is there. A piece of metal of mass 3.6 kilogram is suspended from a spring. What is the reading of the balance? That is the spring balance in Newton. A, with the metal in air. B, with the metal in water. C, with the metal in brine. D, what is the density of a liquid in which it gives a reading of 33 Newton? Take the density of brine to be equal to 1,200. This is 12,000 kilogram per cubic meter. and take the density of metal to be 9,000 kilogram per cubic meter. So 6 minutes for this. 6 minutes for this question. Start with. Of course, the dense acceleration due to gravity is also 10 meter per second squared. J is 10 meter per second squared. Frank, just copy the solution and then go through. If you have any issues with a particular step, you let me know to address it, okay?
Okay, sir.
or 3 minutes more. Two minutes. 2 minutes. Okay, your time is up. But have you managed to finish it? Were you able to finish? Class, give me feedback. Did you finish?
No, please.
Or then hurry up. Another 2 minutes. Additional 2 minutes to finish it. Melda, hurry up. I've given you additional time. Trim,
Yes, sir.
Your hand is up. Have you finished?
Yes, sir.
Okay, we'll discuss it, so don't worry. Okay, so what's your answer for the first question? What is the reading of the balance in Newton A with the metal in air? Yes,
Sir, please. 35.28 Newton.
35.28 Newton, approximately 36.
Yes.
Okay, we shall discuss it. So, what about B?
Sir, in water is 31.36 Newton.
Sir, this is 32 Newton.
Approximately 32.
Yes.
With the metal in brine,
Negative 11.76 Newton.
31.2 Newton.
it should be 31.2. Yes, we'll solve it. Then, what is the density of the liquid in which it reaches 33 Newton? Whoever managed to solve this. What's the density of the liquid in which it gives a reading of 33 Newton?
750 kilogram per meter.
Come again.
750 kilogram per meter cube.
Oh, sorry, something is wrong.
Sir, please, 582 kilogram per meter cube.
Sorry, something is wrong. Anita and Co, Quentiwa, Yasmin and Co, let me hear from you. All right, so let's solve it. The D is 7,500 kilogram per cubic meter. So let's look at it one after the other. So the mass is 3.6 kilogram. We are to determine its weight in Newton with the metal in air. Okay, so the real weight. The real weight. Real weight in air, the tension, the balances, the reading of the balance is equal to its apparent weight. Okay, and that is also equal to the tension in it. So in air, the reading must be equal to its weight. So reading of balance must be equal to the mass times acceleration due to gravity. The mass is 3.6 kilogram. Acceleration is 10. So we must have 36 Newton as the reading of the metal in air. So please start marking whatever you were able to do. II or the B. Okay, it's been lettered A, B. B. With the metal in water. So when it is immersed in water, the apparent weight is equal to the reading of the spring balance. So the apparent weight would be equal to the real weight minus upthrust. The real weight is 36. Updraft is equal to this is suspended in in water. So density of water, okay, 1 or 1,000 times the volume of water that will be displaced. Okay, how do we determine the volume of water that will be displaced? Yes, Nana Kwame Osafo.
Sir, what does the AW stand for?
Apparent weight. The
Okay.
apparent weight is equal to the reading of the balance.
Okay.
Are you okay?
Yes, sir.
Okay. So we need to find the volume of water that will be displaced. Gideon, let me take over. I'm coming in. Now, the volume of water that will be displaced will be equal to the volume of the object, since it is fully immersed in the liquid. Okay, so the volume of the object is equal to its mass, which is 3.6 divided by its density, which were given as 9,000. And so the volume of water displaced is 3.6 divided by 9,000. This times acceleration due to gravity, which is 10. Therefore, 1, 2, 3. We have another 1, 2, 3. I'm coming. Why are we getting 0? What is wrong? I'm coming. The weight is 36, and we are getting this, the updraft. Let's determine the updraft well. Updraft is rho Vg. Okay, the density of water is 1,000 because B with the metal in water. So 1,000 times volume of water displaced, which is equal to the volume of the object. Okay, so this is mass over density. 3.6 divided by the density of the object of the metal, we are told 9,000 times 10. What
Yeah,
is,
please, the answer will be 4.
come again?
Yeah, please, the updraft is 4 Newton.
You mean the updraft is not 4?
The answer is, people are saying it is 0. That is 4.
Yes, I want to see what is the problem, because the answer is supposed to be 32. Okay, the apparent weight is,
I have 36.
come again.
Sir,
I have
Hello,
36.
you had
sir,
30.
please,
Hello, I'm listening.
sir, please, when you calculate what you just did right now on the calculator, you get 4 newtons. Then
So please, we are supposed to divide by 9.
the tension in water is the 36 minus 4, which will be the 32 newton.
I'm coming. Let's calculate the updraft well. Updraft in water. Density of water, which is 1,000, right? Times the volume of water displaced. This is, oh, okay, I get you. I get what you are saying. I get what you are saying. So this is 36. You said the updraft will be 4.
Yes,
1,
it's 4
2,
Newton.
3. 1, 2, 3. So we have 36 divided by 9. And that is 4. Okay, so we have 32 Newton are there. apparent weight. And the apparent weight is the reading of the balance. Okay, so it will read, the reading of the scale will be equal to 32 Newton. Please, thanks for the correction. Then C with the metal in brine. So over here, the difference is that we are changing the liquid. In B, it was in water. In C, it is in another liquid, whose density is different from the density of water. The density of brine is 1,000, it's 12,000. It's 12,000. The volume of brine that will be displaced is equal to the volume of the object. So 3.6 divided by the density of the object. Are you okay? Please, class, are you okay?
Yes, sir.
Times acceleration due to gravity, which is 10. So 1, 2, 3, 1, 2, 3. Okay. So multiply 12 by 36 and then divide that by 9. Multiply 12 by 36 and divide that by 9. Anita and Go, I'm listening. And the gentleman too.
48.
That's 48.
Yes, sir.
Okay, so this is 48 Newton. So if the upthrust is 48, then the reading of the apparent weight would be equal to the object's weight in air. The object weight in air, which is 36 minus 48. Okay, that is why somebody called negative. Oh, okay. Okay, I get you. Let's check if there is something wrong with the calculation. So the weight in air is the mass of the objects. Okay, so 12,000. The density of the brine is 12,000. Meaning, oh, no. The value is not realistic. It's not a real value. No liquid will have this density, meaning its density is 12 gram per cm cube. And brine is just salt water. Class, are you listening?
Yes.
Brine is just sea water. So if water has density 1.0 gram per cm cube, there's no way seawater would have 12 gram per cm cube. Maybe it's a typo error. It's supposed to be 1,200 kilogram per meter cube, which was mistakenly taken as 12,000. So ideally, it must be 1,200. If it's 1,200 kilogram per cubic meter, then it will be equal to 1.2, which will be slightly greater than the density of water. So class, instead of 12,000, let's use 1,200 to calculate for the upthrust. Please, are you okay?
Yes, please.
So 1,200 times 3.6 over 9,000 times 10. And this 1, 2, 3, 1, 2, 3. So it will give us 12 times 36. And what is 12 times 36? Twelve times 36.
432.
432. He said 432. 12 times 3. Oh, sorry. 12 times 3.6 rather. 12 times
Sir, please.
12 times
Sir, please
3.6.
4.8. Sir,
So
please
this
4.8.
43.2. 12 times 36 is 43.2. Are we okay? So if even in that case, the upthrust will still be greater than the real weight. So the problem with this is the value given to us, the value of the density of brine given to us is not so realistic. The upthrust is greater than the weight of the object, and so it will read negative. All right. So we've identified where the problem is from. Frimpoma, Frimpong, Adakwa, your hand is up.
Sir, please, it's okay.
All right. Then the Gideon.
Sir, please, if you convert the fraction to decimal before you multiply, you get 4.8.
No, you see, we changed the density from 12,000 to 1,200. Okay. So 1,200 times the volume of the object, which is its mass divided by the density times acceleration due to gravity. So when you do that, you have 12 times 36. Is that not the case?
Yes. Sir, please, but I use 1,200, but I still got 4.8. 1,200 times the decimal form of the fraction times 10.
Multiply 1,200 by 36 by 3.6 by 10, and then divide that by 9,000. Frimpoma, your hand was up.
Sir, please, the volume, the 3.6 over the 9 that's there to give you 0.4. So if you multiply it by 12 to give you 4.8.
1,200 by, you said the volume, let me divide.
3.6, sorry, 3.6. The volume.
3.6 divided by 9,000, right?
Yes, please. Yes, please, times 10. And then.
Then when you multiply that by 1,200.
Yes, please. The 3.6 over the 9,000. Like when you calculate the whole thing, you get 4.8.
8.
Yes, please.
Let's take it again. That's why I asked you to be doing this multiplication for me. But when
Sir, please.
Yeah, I'm
Sir,
coming.
please, you're supposed to divide.
Okay. So yeah, when we divide, we have 12 by, yes, I'm getting what 4.8 as well, as you said. 12 by 3.6. Okay. And that is 43.2. Then when you divide 43.2 by 9, it's 4.8. Oh, okay. Meaning the calculation was rather the problem.
Okay.
Okay. Please, have you seen it? The calculation was rather the problem. When we divide, okay, we have 12 times, even if you multiply 12 by 3.6 and divide by 9, it must give you 4.8. Okay, so the next time I will leave it to you to rather do the calculation rather than not having a calculator around and doing it. Okay. And so when you subtract 36 from when you subtract 4.8 from 36, that gives us, I think, the answer, which is actually 31.2 Newton. Okay. So next time, please take over the calculation and then be doing it. So this will be the reading of the scale when it is immersed in brine of density. Then the next question The D question, we are giving the reading of the balance, the apparent weight. But we are to determine the density of the liquid. Weight in air minus weight in a liquid, or the apparent weight, which is the reading of the balance, must be equal to the apras. Okay, the apras is rho Vg, where rho is the density of the liquid which you are looking for. V is the volume of the liquid displaced, which is equal to the volume of the object or of the metal. Okay, its weight in air is still 36. The weight in fluid, which is the reading of the balance, is given to us, and here we are told it's 33. So minus 33 must be equal to the density of the liquid which we are looking for, the volume of the liquid displaced is equal to the volume of the object. So 3.6 divided by 9,000 times acceleration due to gravity. So all that we are looking for here is rho. So 3 Newton, when we subtract, must be equal to rho times 36 divided by 9,000. So please make rho the subject here for me. Make rho the subject. I'm waiting for your response. Yes, what's the answer? Class, what's the answer? The answer is 750 grams per meter cube. I think, and here too, the book gave the answer as 7,500. It's another typo error. So the answer must be 750 kilogram per meter cube, which is equal to 0.75. Please, class, are you okay?
Yes, please.
So that's the answer for D. Any question here? Is there any question?
Yes, sir.
Yasmin. Yasmin.
Yeah.
Oh, it's a mistake. All right. Please, if you haven't muted, mute yourself. I'm getting. Let me mute all and then. Yasmin, if you have a question, please go ahead and then ask. If you don't have it, then.
Please, can you go over the D again?
Okay. So the D question says that what is the density of a liquid in which it gives a reading of 33 Newton? So here, the 33 Newton given, is the reading of the scale reading. The scale reading is actually the apparent weight of the object in the liquid. Okay, so apras is equal to weight in air which is the real weight, minus apparent weight, which is the weight of the object in liquid. The apparent weight, or the weight of the object in liquid, is the reading of the scale. So we have the weight in air is 36, 8 mass times acceleration due to gravity. So 36 Newton minus the reading of the scale, which is given to us 33. Okay, so it means that the upthrust is equal to 36 minus 33, which is 3 Newton. Now, the same upthrust is equal to weight of fluid displaced. So density of the fluid times volume of the fluid displaced times gravity. In this particular question, the density of the fluid is what we are looking for. So rho is not known. The volume of the liquid displaced is equal to the volume of the object because the object is fully immersed in the liquid. We have the volume of the object to be 3.6 divided by its density, which is 9,000, times acceleration due to gravity, 10. So it means that we have rho times 36 over 9,000. So you can determine 36 over 9,000 or make rho the subject by eliminating the denominator. When I multiply through by 9,000, I have this canceling this. So I have 36 times rho is equal to 9,000 times 3. Then we divide through by 36. When you do that, you have 3 going into 36, 12. So 9,000 divided by 12 is equal to 750 kilogram per meter cube. Yasmin, that's how we got the answer. Are you fine?
Yes, sir.
All right. One last question. There's a second one, but that will be given to you as an assignment. A hot air balloon has a volume on the ground of 10 meter cube. A hot air balloon has a volume on the ground to be 10 meter cube. So the volume on the ground is equal to 10 meter cube. And the balloon fabric weighs, so weight of balloon. The balloon fabric weighs 80 Newton. The balloon fabric weighs 80 Newton. It is filled with hydrogen gas of density. It is filled with hydrogen gas of density, so rho of hydrogen. The density of hydrogen is 0.09 kilogram per meter cube. It is filled with hydrogen gas of density 0.09 kilogram per meter cube. And the air density, so the density of the surrounding air is 1.2 kilogram per meter cube. The density of the surrounding air is 1.2 kilogram per meter cube. Estimate the maximum weight. Estimate the maximum weight additional to that of the hydrogen and the balloon fabric, which the hot air balloon can lift. Estimate the maximum weight additional to that of the hydrogen and the balloon fabric, which the hot air balloon can lift. So, having given all this, we are to estimate the maximum weight which can be added to the hot air balloon with the weight of the balloon and then the hydrogen gas and everything. Please, is the question clear?
So are we finding the maximum weight or the weight that can be added?
The weight that can be added. The maximum weight that can be added to the balloon. So if I earlier told you that the hot air balloon is used for tourism and for exploration. So it takes people on board. So you are giving the weight of the balloon itself, and you are also giving the weight of the hydrogen gas within. In addition to this, you must add weight or put people on the balloon. So weight of people, P. The total weight of the balloon itself plus the hydrogen gas plus the people or the additional weight or load must be equal to the upthrust provided by the surrounding air. And this is the principle guiding the whole thing. So we are saying that let additional weights be equal to WP, whichever way you want to, represent it. Let the additional weight be equal to WP. So WB is the weight of the balloon itself. WG is the weight of the gas within, hydrogen gas within, plus the weight of the additional load or people that will be put on board. All this must be equal to the upthrust. That is it. So this is the key to the question. So determine the weight of the balloon itself, and that is given 80. And determine the weight of the hydrogen gas, and WP is what we are looking for. When you finish, you calculate for the upthrust that will be produced by the surrounding air. Then you subtract this sum from the upthrust, and you are good to go. So try it, and then let's see. So WP would be equal to U minus WB plus WG. That's the key to the question. So try it for 5 minutes and we will discuss it afterwards. If you have any questions.
So before you do the last part of the question, the maximum weight.
So estimate the maximum weight additional to that of the hydrogen and the balloon fabric, which the hot air balloon can lift. Okay. Estimate the maximum weight additional to that of the hydrogen gas and a balloon fabric which the hot air balloon can lift? That is the question.
So thank you.
Welcome. I'll be with you after the 5 minutes, okay? Just give it a try. We'll discuss it afterwards. Right? Just do what you can. So I'm sure you are true. Hello. So
Almost.
let's determine the appras. The appras is equal to density. You see, the appras is for hot air balloon. The appras is produced by the surrounding air. So the density of the surrounding air times volume of air displaced times acceleration due to gravity. Okay. The density of the surrounding air is the 1.2, but let me check the units because density, let me check as how it was given to us. As to whether it was given in gram per cm cube or kilogram per meter cube. Okay, so a balloon has a volume on the ground of 10 meter cube, and the balloon fabric weighs 80. It is filled with hydrogen of density 0.09 kilogram per meter cube. Okay. And the air density is 1.2. Okay, so it was given to us in kilogram per meter cube. Okay, so 1.2 times, what do you think will be the volume of air displaced? Class, what will be the volume of air that will be displaced? Anybody to
10 meter cube.
why will it be 10? Why will it be 10?
10.
Why 10?
10.
Yes, why 10? Is there any reason why you think it will be 10?
Because the weight of the volume of the balloon is 10 meter cube.
So, yes, the object will displace volume of air, which is equal to its own volume. So 10, thank you. Times acceleration due to gravity, which is also 10. Therefore, the appras will be equal to 120 Newton. Please, did you get that?
Yes, sir.
Okay, so we have the weight of the balloon. So let's determine the weight of the hydrogen gas. That will also be the density of the hydrogen gas times volume of hydrogen gas times gravity. Density of hydrogen gas is 0.09. What about the volume of the hydrogen gas? What will be the volume of the hydrogen gas?
10.
Why 10? Why 10, class? I always admire these reasons. Why will the volume of the hydrogen gas be 10? Any reason?
The volume of the object is the same as the volume of the air it displays.
The thing is that gases take the shape of its container. Gases do not have a fixed shape and volume. Yes, they may have its own volume, but they always take the shape of its container. So if you fill any container with gas, the volume the molecules expand and then fill the shape of the container. That is why the volume of the gas will be equal to the volume of the balloon fabric itself. Okay, so that's the reason. So 10 times acceleration due to gravity, which is also 10. This would give us 9 Newton. Therefore, the additional weight WP must be equal to the upthrust, which is 120 minus the weight of the balloon, which is 80, plus the weight of the hydrogen gas, 9. So 120 minus 89. And class, what is 120 minus? This is 31 Newton. Meaning, what it means is that the additional load or weight that can be put on the balloon and still be able to float or move the maximum must be 31 Newton. Anything greater than 31, the balloon cannot go up. That's the reason or the explanation. Anything greater than 31 Newton, the balloon cannot go up into the airspace to float. Any question? Class? All right. Okay. This is the last question which you have to do submit as an assignment. We have about 10 minutes to end the lesson. Okay, so I expect you to start answering this question. If you are not able to finish within the 10 minutes, just finish it and send it to me as an assignment. Okay, and I'm dropping it on the platform. I'll read the question with you. Please, the question is sent to the platform. A balloon, similar question to what we just saw. A balloon of volume 2,000 meter cube. A balloon of volume 2,000 meter cube is filled with hydrogen of density 0.09 kilogram per meter cube. If the mass of the fabric is 100 kilograms and that of the pilot is 75 kilograms, what will be the greatest mass? What will be the greatest mass of equipment that can be carried when operating in air of density 1.25 kilogram per meter cube? So the first question is that what will be the greatest mass of equipment that can be carried when operating in air of density 1.25 kilogram per meter cube? How will this figure change if helium, which has twice the density of hydrogen, under the same conditions were to be used? How will this figure change? What figure are we referring to? We are referring to the greatest mass of equipment. Okay, so if we this time around fill the hydrogen, the hot air balloon with helium, how will this figure change? On condition that helium has a density which is twice the density of hydrogen, how will it change? Okay, so please, still the weight of the balloon plus the weight of the pilot or the people plus the load must be equal to the upthrust. The upthrust produced by the surrounding air. So it is based on this same principle. The balloon, the gas within, plus the people, plus the equipment. Here, the people, they only talked about the pilots. So the balloon fabric, the gas, the pilots, plus the equipment that must be added, this must be equal to the upthrust produced by the surrounding air. So this is your assignment. Try it right now. I have another class. That's why I'm giving the question to you. Try it using the minutes left. And then if you are not able to finish, do it and then forward it to me as an assignment. Please, is there any question? Class, is there any question? Okay, if there is no question, continue with the assignments and we'll continue. When you finish, forward it to me. We'll continue our discussion next week. Next on Tuesday, Thursday. Thursday, we'll start a new topic. Ferdinand.
Sir, please, can you send the question to the
group? It's on the group. I just forwarded it.
Okay. Thank you.
All right. Okay, so until then, may the good Lord be with you and bye-bye. All right. I have another class, so I need to go. But please finish and send it.